Section 5, we're going to be doing application problems. So in order to work on these problems, first thing we should do obviously is read the problem. If we can, we'll go ahead and we'll make a picture. We need to figure out what we know and what we don't know. If we don't know something, we're going to assign it a variable, and we'll label our picture best as possible. Then we're going to make some equations out of what we've been given in the reading of the problem. And we're going to attempt to maximize and minimize, which means we need to be able to write these equations, or one of the equations anyways, in terms of only two variables so that we can use our derivative to find our max or min. So for our first example, a carpenter is building a rectangular shed with a fixed perimeter of 54 feet. What are the dimensions of the largest shed he can build, and what is the area? Okay, so they're talking about perimeter, so we're going to be talking about the shed with the largest base. It says it's rectangular, so here's our rectangular shed. Okay, what we do know about a shed is it has a length and a width as far as a rectangle is concerned, but we don't know anything about the length and the width, so we'll go ahead and make this side length, or width rather, I'm sorry, this side length. We do know that it has a fixed perimeter of 54 feet and that they're asking us about area. So perimeter is distance around the outside. Since opposite sides have the same measure, it'll be 2 times the dimension of the width plus 2 times the dimension of length. That's going to give you perimeter. Happens to equal 54. That's been given. Also, they're talking about area. So area is going to be equal to length times width. So if we maximize the area of the base, we should maximize the size of the shed. Problem is, this is in 3 variables. I need to be able to rewrite this using area and then only one other variable on the other side. This is the equation. This is the constraint. Perimeter has to be 54. We're going to use this one to solve for one of the letters, so that we can replace one of these with the other and be all in one letter on the right hand side. First, since everything's even here, let's divide all terms by 2. So 27 is equal to W plus L. Let's go ahead and solve it for L. We'll subtract W. So L will be equal to 27 minus W. This is good. This means in the area formula I can replace the L with the expression 27 minus W and be only in 2 variables. So area will be equal to 27 minus W times W, and when we distribute it'll be 27W minus W squared. Since we want to maximize the area, let's go ahead and use the derivative. So A prime derivative of 27W is 27 minus the derivative of W squared is 2W. If I set this equal to 0, I'll be able to find out where there is a horizontal tangent line, which would occur at a max or min value. So we'll add 2W to both sides, so 2W will equal 27. Divide by 2, W will be equal to 13.5. Question is, do we have a max or min value here? So 13.5 splits our interval. We're going to use a test value on the left and a test value on the right. Put those into the first derivative. First derivative for 12 would be equal to 27 minus 2 times 12, which is 24, so this is 3. So positive, therefore we're increasing on the left of 13.5. If we throw 14 in the first derivative, we have 27 minus 2 times 14, which is negative 1. So we're negative on the right-hand side, which means we're decreasing. So at 13.5, we've made the change from an increasing tangent line to a decreasing tangent line, which means at 13.5, we did find a max value. So then if the width is going to be 13.5, I'm going to go back up to this equation where it says L is equal to 27 minus W, and replace the W with the 13.5, and that means the length will also be 13.5. So apparently this is going to be a square shed. So we're going to maximize this area. It's going to occur when the shed is 13 and a half feet by 13 and a half feet. Okay. Okay. We read our problem, drew our picture, labeled it with variables what we didn't know, wrote down the information that we did know, talked about perimeter, talked about area, put down their formulas, made a substitution with what they gave us, and then we use this constraint equation to solve it for one letter so that we could rewrite our area equation in terms of just 2 letters instead of 3. Then we use the first derivative to find our local max, local min values. We tested to make sure it was what we wanted it to be, and then we used it to solve for the other dimension that was asked. Now, did they ask? They asked for the area. That's the one thing we haven't done yet. So then the area is length times width, so 13.5 times 13.5 is going to be 182.5 feet squared. And that will be the maximum area.